Chapter 8 is concerned with experimental and quasi-experimental designs. Experimental and quasi-experimental designs both require that the researcher actively intervenes to bring about the desired effect. They test cause and effect relationships and provide level 2 and level 3 evidence on our pyramid. So it is the best type of design for quantitative studies. There are 3 criteria that are needed to infer causality. One is that the causal, or the independent variable, as we've been talking about, and the effect, or the dependent variables, must be associated with each other. 2, the cause must precede the effect, such as smoking must come before the lung cancer, not vice versa. And 3, the relationship must not be able to be explained by another variable. Now I want you to memorize this. A true experimental design has 3 properties: randomization, control, and manipulation. In hospital and clinic settings, this is referred to as a clinical trial and is commonly used in drug trials. It is the gold standard of all quantitative studies, meaning that you have more confidence that the intervention was effective and will produce the same effects over time. Randomization means that each subject in the study has an equal chance of being assigned to the control group or to the experimental group, and it assumes that any important intervening variable will be equally distributed between the groups, minimizing the variance and decreasing selection bias. Now, in the slide, I want you to pay particular attention to the right-hand side. The first R, it stands for random selection. That means that you have chosen them using a specific plan from the population. The second R is random assignment, meaning out of that group that you randomly selected, you then once again randomly select out of that sample people to be in your control group or in your experimental group. Observation 1, or O1, is generally when you collect data pre-test. The X is the treatment, and observation 2 is the test after you've done the treatment. To be a true experimental design for my course, random selection must be used to get your sample, and then random assignment must be done to divide it into the control group and the experimental group. Now we want to talk about control. Control is introducing one or more constants into the experimental situation. It is acquired by manipulating the independent variable, random assignment, using a control group, and the control group, remember, gets either the usual treatment or a placebo. Control involves the imposing of rules by the researcher to decrease the possibility of error and increase the probability of the study's findings being an accurate reflection of reality, and it's implemented throughout the design. The stronger the design, the more accurate the findings, and the greater the ability to predict and control the phenomenon under study. There are various ways to achieve control. One of them is controlling those little pesky extraneous variables. Extraneous variables, if you remember, confound the relationship between the independent and dependent variables and that needs to be controlled by the research designer, sometimes through statistical procedures. For example, a nurse researcher wants to know if monitoring blood glucose levels and exercising will result in a decrease in hemoglobin A1C levels of individuals with type 2 diabetes. The independent variable is monitoring of blood glucose levels and exercise. The dependent variable is the hemoglobin A1C levels. The researcher would want to have the subjects in the study all be the same so that diet, severity of disease, level of physical fitness, and all other things that impact blood glucose would be controlled, so then the results would be valid. In other words, controlling extraneous variables enables the researcher to accurately determine the effect of an independent variable on the dependent variable, which is also known as the outcome variable. Another way of having control is by controlling the sample. Now, sampling is a process of selecting subjects who are representative of the population being studied. Random sampling usually provides a sample that is representative of a population because each member of the population is selected independently and has an equal chance or probability of being included in the study. For example, if a researcher was interested in a population of individuals with type 2 diabetes who lived in the city of Chicago, first she would have to find all these individuals and then use a procedure to randomly pick a group to participate in the study. Now, I want you to think about this. How in the world are you going to find all of these people? Remember that random sampling is different from random assignment. Random assignment is randomly selecting subjects to be placed in a treatment group or one that is not to receive the treatment, but random selection increases the control to even a greater extent and gives the findings more validity or truth. You can also control the setting, and there are 3 types of settings in which research is conducted. There is the natural setting, and this is the place where the researcher does not manipulate or change the environment for the study. For example, a researcher may conduct the above study on exercise with diabetics, but use the exercise equipment at gyms of the subject's choice, and this could impact the results. Or she could use a partially controlled setting, where the researcher modifies the setting to a degree. For example, in the diabetic study, exercise may be done at a gym, but the equipment is not calibrated, and this could impact the result. Or she could use highly controlled settings. This is an artificially constructed setting created especially for conducting research. For example, the exercise component of the study could take place in an exercise physiology lab where all of the equipment is calibrated and the METs for the exercise are actually measured. Obviously, this gives the research the most control. You can also control the measurement tools, making them more precise, valid, and reliable, and controlling the independent variable. This means that each subject would get the very same treatment, so changes in the outcome can be contributed to the treatment. For example, think about doing an experiment using a drug to control hypertension. If you gave different amounts to different subjects, you would not know if the drug caused the change in the blood pressure or the different amounts of the drug caused the change. 7. Manipulation is just plain doing something to at least some of the subjects. The independent variable is manipulated when some subjects, the experimental group, receive the intervention, and when others, the controlled group, does not. Doing something may include such things as giving a drug, providing education about a disease, or counseling subjects who have anxiety, and a multitude of other things. This is a flow chart of a randomized clinical trial. In the first box, the sample should be selected randomly. Then demographic variables are collected or baseline data, and pretests are given, and then the subjects are randomly assigned to an intervention group or the group that does not give the intervention. Then data are collected after the treatment is administered to the intervention group, and data are collected from the control group to see if there are any differences. Now, randomized clinical trials use experimental and control groups, and they have a very specific sampling plan using inclusion and exclusion criteria. And we're going to go into more detail about this when we get to the lecture on sampling. Now, they also have intervention fidelity, which ensures that every subject receiving the intervention receives the identical intervention. Randomized clinical trials also use statistical comparisons to determine if there are any major differences between the groups, because that can affect the outcome variable. And remember that sample size is important too. If it's too large, it wastes time, resources, and money. And if it's too small, it can lead to inaccurate results. Sample size. If the sample size is too small, differences may not be detected, resulting in a type 2 error. And we're going to talk about type 2 errors when we get to statistics. And determining the right sample size is called a power analysis. And researchers should always provide information in the article that the sample size was accurate. Classical randomized clinical trials usually involve these steps. 1, they get a representative sample recruited from their population of interest, let's say the city of Chicago with type 2 diabetes. Then they measure demographics, and they measure the variables of interest, dependent variables, such as the hemoglobin A1C, before they do the intervention. Number 3 is the participants are then randomized to the experimental or to the control group. And number 4, measurement of the variables of interest, the dependent variables, in this case it would be our hemoglobin A1C, are collected to assess the effect of the intervention. And this is basically the randomized clinical trial team. Now, the randomized clinical trial is a strong design for testing cause and effect relationships. However, there are a couple of others that we're going to look at. There's the Solomon 4 group and the after-only design. The Solomon 4 group design randomly assigns your subjects to 4 groups. There's an experimental group, a control group, an experimental after group, and the control after group. The experimental after group and the control after group receive no pretest. They only get post-test. It controls for the testing effects that are a threat to internal validity. And the only reason it's not done very often is because it is very expensive and requires a larger sample team. This is a flow chart of the Solomon 4 group design. As you can see, the top 2 groups are just the same as our randomized clinical trial. The bottom 2 groups are used to show that the change after the intervention is not because of collecting data beforehand. For example, if you were giving a pretest on attitudes about an emotionally charged subject such as euthanasia, the pretest may change the opinion even before the education program is given as an intervention. So we need to know about the effect of the pretest on both the treatment group and the control group so the effect can be statistically removed. And as I said before, it's hardly ever done. I've never seen it in any of the literature, and I've been reading the literature a very long time. This is the after-only design. It is a post-test only control group design. There are randomly assigned experimental and control groups, but neither is pre-tested nor are they measured. but it's particularly useful when testing effects are suspected to be a potential major threat to internal validity. And this is the flow chart of the after-only design. This design is the weakest of the experimental designs because pre-testing is not done before the intervention is given. For example, if you were decreasing salt intake to reduce blood pressure and did not assess the blood pressure before doing the dietary intervention, how would you know if decreasing the salt intake actually decreased the blood pressure? Maybe the treatment group had low blood pressure at the start, and decreasing sodium then had no change would be seen in your study, and you wouldn't please the blue suits, when actually there might have been a significant change that you could not find. The strengths of the experimental design. It is the most powerful design for testing cause and effect relationships because it uses control, manipulation, and randomization. What that means is there are fewer things that can come in and muck up your study because of the control, giving the intervention, and using randomization. 20. Well, there are weaknesses in the experimental design. It may be very complicated and very expensive to conduct. It might be difficult or impractical for certain clinical settings or because of ethical considerations. It would be very unethical if you wanted to study grief reactions in women and killed their husbands in order to have enough subjects to study. Besides being like the researchers in the unethical studies we have looked at, you'd be in jail. Quasi-experimental designs also test cause and effect relationships. Randomization may not be possible, or there might not be a control group. And lack of control group makes evidence provided by quasi-experimental designs less convincing. It provides level 3 evidence. So what this slide is trying in essence to say is that quasi-experimental studies, at least one of the hallmarks of experimental studies, randomization, manipulation, or control, is missing. Most often, the randomization piece is the one that is missing, too. There are several types of quasi-experimental designs, and the first one we're going to look at is the non-equivalent control group design. It has an experimental and control group, but no randomization. The threats to internal validity include selection, maturation, testing, and mortality. The results of this study are still relatively strong because the researcher is able to compare the two groups on antecedent variables before the intervention. This is the non-equivalent control group design flowchart. And an example using this flowchart might be the following. You as a nurse manager want to see if a Keep Healthy program will reduce the number of sick days that your staff take. So you determine the number of sick days that your staff takes, and then determine the number of sick days that a sister unit takes. And this is the collection of data at baseline. You then provide your staff with the program and count the number of sick days. You also count the number of sick days that the sister unit had during the same time period. There was a significant difference between the number of sick days taken, and it really looks like the program worked. But wait a minute here. What we do not know is what the groups looked like ahead of time. Maybe your unit all got flu shots, which would cause a decrease in the number of sick days. And maybe the other unit did not. So the number of sick days was actually related to the flu shot and not your intervention. Another quasi-experimental design is the after-only non-equivalent control group design. Randomization is not used and makes the assumption that experimental and control groups are equivalent before the introduction of the independent variable. Confidence in the findings depends on the integrity of this assumption that the two groups are comparable. And this is the flow chart of that after-only, non-equivalent control group design. An example of this would be the following. Again, you as a nurse manager want to see if that Keep Healthy program reduces the number of sick days that your staff will take. So you provide your staff with a program, count the number of sick days. You also count the number of sick days that the sister unit had during the same time period. There was a significant difference between the number of sick days taken, and it looks like the program worked. But wait a minute here. Who knows what the number of sick days were before the program in either unit? Maybe your unit does not really take that many sick days to begin with. Or perhaps the nurses on the sister unit are older and have little kids and therefore may take more sick days because of herniated discs, etc., or their kids got the flu and they took sick days to care for them. We would never know because the information was not collected ahead of time. And then we have the one-group pre-test, post-test design. This is used when only one group is available for study. Only an experimental group and data are collected before and after an experimental treatment. There's no control group and no randomization. This is a really poor design. And this is the flow chart for the one-group design. All kinds of things can wander in here and muck up the study. There's no randomization and there's no control group. Finally, there's the time series design. This design is useful to determine trends over time. Data are collected multiple times before the intervention to kind of establish a baseline. And then data are collected multiple times afterward to determine the change from baseline. Testing, maturation, and selection are all potential threats. And here's our flow chart for the time series design. This is a bit stronger than the one-group design because it is repeated a number of times. Using our Keep Healthy program, the manager collects data on the number of sick days taken over several months, then institutes her program and counts the number of sick days taken for several months after the program. And if you look at the bottom of the slide, you can kind of see a chart where you had a very high number of sick days before the intervention. Then it dropped down and stayed down, which kind of gives further proof that your intervention actually worked. Now, the strengths of quasi-experimental designs is that they're practical, they are less expensive, and sometimes they're the only feasible alternatives because these designs are more adaptable to real-world settings, and replication of the study can strengthen the evidence. However, there are weaknesses of quasi-experimental designs, and the biggest one is it is unable to demonstrate clear cause and effect relationships. So now I'd like to go on to the next lecture, which would be in Chapter 9.